Okay, cool. Hello, everyone. My name is Jesus Najera, aka SetDev, aka SetZeus, and I'm the owner and founder of SetDev, which is a Bitcoin and Bitcoin L2 contracting and security company. And we occasionally make our own products as well, one of which is BitScript, which I will be using today for the talk Introduction to Script. So quick, I'm curious to get like a gauge here because I assume this is a pretty technical crowd. Who here has written script at any point in their career? Okay, cool. So yeah, I want to make it clear this talk is definitely, the audience is more targeted towards either non-technical, semi-technical, or developers and programmers that are technical but are curious to learn more about how script actually works underneath the hood. And without any further ado, I'm going to get into it. Cool. Okay, so today's agenda, we're going to start with the very, very basics of script, such as why learn, how does it work, what exactly is it. We're then going to dive into some syntax, and then we are going to wrap up with some examples, which if you have your laptop, you're actually going to be able to follow along, as long as you have Chrome as well, because I realized a bug in Firefox earlier today. Cool, so why bother learning script? First off, well, context for the next opcode. We are at OPNEXT after all. And so if you don't know what an opcode is, I highly doubt you have the context to understand what is the next opcode that should be activated. And so that is probably the number one reason for giving this talk. I actually had the privilege of giving this talk in Boston for the very first opnext.dev conference. And I got feedback that it was really, really useful context for the rest of the talks. Because again, most of them are focused on presenting all the different options for the next opcodes, et cetera, et cetera. Me personally, I like keeping up with that dialogue and temperature check, usually the website that I have linked up here. And again, you guys can see this is where a lot of the veteran engineers, people who have been here for years, are sort of giving their opinion on what they believe should be activated. And yeah, so I mean, that is probably the number one reason for giving this talk, so that you guys have context for all the talks that come after this, that come tomorrow, etc. And one more thing is I really want to make this much more of an educational talk than anything else. So everyone that's here to learn, if at any point I rush through something or something is unclear, please, please, please feel free to raise your hand. Go ahead and call on you and we can have a dialogue. At the end of the day, this is mainly for you. If you are one of the many senior or veteran engineers that are in the crowd, and I say something that is, not precise or even nonsensical, please also raise your hand and let me know, because again, we're always learning here. So, context for the next op, and why else should you bother learning script? Well, real simply, script is what moves Bitcoin around. And so when you send Bitcoin from one wallet to another, that isn't technically what's happening underneath the hood. And obviously we're here for a technical discussion. And so what really happens is you have a collection of UTXOs, or unspent transaction outputs that you want to spend. And when you spend them, what actually happens is you transfer the ownership through some cryptography from one or more public keys to another public key. And so UTXOs have a lock around them. And that lock, or those set of instructions, are typically called the script pub key. So if you go to mempool, or if you go to any of the other block explorers, you'll usually see script pub key. On the other side, the inputs provide the unlock script, or the instructions to unlock a specific UTXO. And so these sets of instructions are what we call script. One of them throws a lock around it. One of them unlocks that previous lock. Okay, and so before we get into the actual syntax, I want to review two high-level concepts that are really, really critical to understanding how this all works together. And again, hopefully everyone here has at least heard of inputs and outputs. But if you haven't, every transaction includes inputs, every transaction includes outputs. And what happens is with every input, it points to a previous UTXO, or an unspent transaction that was already mined. It fetches it, and then it fetches the lock script for it, and the input that you're submitting has an unlock script with it, right? So here we can see in the input, which is the top one, we have a transaction ID, because again, we need to point to the UTXO that was spent. So hey, on what transaction was this UTXO spent? We have the vout, which points to what specific UTXO in that transaction. So the transaction has, hundreds of UTXOs. Which one are you actually trying to unlock? And then you provide the SIG script with which, again, for the concepts of this discussion, the SIG script is the unlock script, or basically what unlocks the lock from the output. On the bottom, as you can see, we fetch the output, and we can see the amount of Bitcoin. We can see the size, which size will make more sense after this talk. And then we can actually grab the pub key script, or AKA the cryptographic lock around that input, around that Bitcoin. And so what happens is we provide a SIG script, the unlock script. We grab the lock script, which is the script pub key, and we attempt to execute them in serialization. And if the protocols, if a node knows that, hey, this was actually unlocked correctly, then that is considered a valid Bitcoin transaction and is therefore propagated to the rest of the network. Okay, so in addition to inputs and outputs, there's one other concept that I think is really, really key background, and that is the concept of a signature, aka a digital signature. It took me some time to really let this sink in, but I forgot exactly who said it, but you can basically think of Bitcoin as a linked list with digital signatures. They are that important to the entire protocol. And a digital signature, again, it's really, really simple to think of it in terms of its analog equivalent, right? So when you sign something, you are signing some message, and you specifically are signing that with, a pen. And so, for example, that message can be many things. It can be a business contract between two people, or it can be a check, which with obviously the message in the check is the amount, the bank account, the specific account number, when it expires, etc. And so in Bitcoin, you are also providing, when you provide a digital signature, you are signing a message, and that message is typically a specially formatted version of the transaction. And the pen itself is your private key. And so that's where the saying, not your keys, not your coins comes from. Because if someone actually has your private key, well, then that someone else can actually sign on your behalf, and the network can't tell that it wasn't actually you. Someone else has your private key. And the reason why digital signatures are, well, the reason why I want to introduce this before getting into the syntax is because not every, but almost all transactions, the final step before they're actually executed is to verify that the signature is correct. So we need to verify that, again, the message is this special format of a Bitcoin transaction, and that the private key matches the public key that this was signed with. And as you guys will see, this leads to one of the more common and most important opcodes. Okay, so now before I move on to the syntax, I'm curious if there are any questions so far about just inputs, outputs, and signatures. I don't believe so. No? Okay, cool. But I guess my question there would be, if it doesn't have a signature, it's probably a non-standard transaction, right? Okay, and are those always broadcasted? Ah, okay. Okay, so now moving on to syntax. Okay, script, really simply, is an array of bytes expressed in a hexadecimal format. And so you guys are seeing there a really, really basic example of a script, which I'll come back to in a second. But you can think of a script as, well, sorry, every script has basically only two things at the very, very highest level. It either has data or it has an opcode. And so as we talked about, what's an example of data? Well, again, if you want to verify a signature, you need the signature and you need the public key. That counts as data. If you want to do some math operation on it, math or like numbers being pushed to the stack also counts as data. And on the other side, you have opcodes, which again, those are functions, command, operations. and the main topic of this conference, right? Which opcode are we going to activate? Okay, so now let's talk a little bit about how these scripts are actually interpreted and executed. There is, quote unquote, an engine, which is called the stack, which is just a very, very simple programming structure that follows a last in, first out life cycle. So you guys can see to the right that we have an empty box, and you can think of it as a box, and we're going to push items to that box. And in core, the stack and opcodes are primarily handled in a file called script/interpreter.cpp, if you guys actually want to see underneath the hood of this engine. And one thing to realize, and this trips up a lot of developers up when they're first getting into this, the stack is sort of dumb. It's really, really, really limited, and it cries and complains about everything. And so that being said, if you want to push data to the stack, you first actually have to tell it the exact size of the data that you're going to push. So back to this very first script I showed you guys, I split it up into two different parts. You can see 0x20 and then 0x31 blank, 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 blank. And so what's happening here is, you guys can see on the left side, we are saying, hey, stack, we're about to push 0x20 bytes to you. 0x20 in hexadecimal is equal to 32. So this actually translates to, hey, stack, we're about to push 32 bytes to the stack. Cool. So again, data and opcodes are pushed to the stack. They're consumed one at a time. Sometimes data is pushed back. Sometimes data is destroyed. But the most important detail to note here is, in order for a transaction to be considered valid in Bitcoin, at the end, the stack should have a single item in there, and that single item should be the number 1. As long as 1 is at the top of the stack. Okay, copy. Well, you need 1 all the way at the top in order to make it spendable. Okay, so there you go. So going on from that, what are the different opcode categories that we see? And so now we're getting into the actual opcodes themselves. And these are all the common categories of opcodes, which I'll show you guys some basics examples. But we have, starting with crypto, which does not mean crypto coins or anything like that. It stands for cryptography. So for example, verifying a signature, opchecksig, or hashing. So hash 160, hash 256, SHA 256. These are all opcodes that work within the scripting language. You have flow opcodes, which if you come from any other programming language, there's always conditional ways of flowing. So for example, if, else, and, or really, really basic functions. We, of course, have math opcodes. So adding, subtracting, maximum, minimum, something's equal, equivalency. Those are all math codes. And then we have push opcodes, which again, as I mentioned, whenever you want to push data to the stack, you first need to tell it, hey, I'm about to push X amount of bytes to the stack. Last but not least, there are a set of functions or opcodes that are native to the stack structure. And I'll be showing some of them, but to give you an example, some of them is, op duplicate or op swap, op depth. And so here you guys can see just a few of the common opcodes in each category. So checksig, hash 160, hash 256. And you guys could actually see to the right of it, the hexadecimal expression of these opcodes. So going back to the script examples that we're going to see, this is exactly how you can tell which opcode you are looking at. Okay, so that was a pretty high-level introduction to script. But now I'm going to show you guys some examples of how these actually work and how they're executed. And again, if you have your laptop, feel free to take it out now because we're going to be jumping into an IDE. And before I do, any questions at this point? Okay, cool. So again, if you have your laptop and if you have Chrome on your laptop, head to bitscript.app, which is again a tool that me and my team built out mainly for gaining our own understanding of script a little bit further. And you can click develop. we have a few advanced tools: script sandbox, transaction deserializer, a hashing calculator, data formatter, multi-sig generator. Today, we're obviously going to stick in the script sandbox. And so I'm going to show you guys some very, very simple scripts, and we're going to get increasingly more complicated. So let's start by just simply adding two numbers. So we're going to type in the number 1, enter. And as you guys can see, when I type in the number 1, this IDE actually prepended and showed us op push 1. Again, we're about to push the number 1 to the stack. The stack is dumb. We need to tell it, hey, man, we're about to push 1 byte worth of data. Let's say we add the number 2, enter. Again, the number 2 is also represented with 1 byte. So we are still telling it, hey, stack, we're about to push 1 byte worth of data to you. And to the right, you can actually see how the stack is being filled in that LIFO structure. And then last, let's go ahead and actually explore our first opcode. So we're going to go ahead and do op add. And you guys can see to the right, what's going to happen is we have both of these two datas. It's going to consume both of them, and it's going to push back 0x03, or the number 3, to the stack. And just continuing with this really simple example, let's go ahead and type in the number 3 as well. And obviously, all we're going to do right now after we add is we're going to add number 3. And now we're going to do one of the two equivalency opcodes. So there's actually op equal and op equal verify, and they do not do the same thing. So first, op equal. If two items are equal, it returns the number 1. If they are not equal, it returns the number 0. So in this first example, 3 and 3 are equal. It's returning the number 1. Okay. Fairly simple. Any questions at this point? Cool. All right, so now let's get a little bit more complicated with it. We're going to start with the number 1 again. Except this time, we're going to add 1,000. And as you guys can see, this time around, we do not see op push 1, but we actually see op push 2. And that's because the number 1,000 cannot be represented by 1 byte, but it's actually represented by 2 bytes. And so now we see op push 1, the number 1. Now we're telling the stack, hey, we're about to push the number 1,000, which is 2 bytes worth of data. So we see op push 2. And now we see the number 1,000. And we're going to do the same thing. So op add. And again, we're obviously going to see the number 1,001. I want to, below that, add in the number 1,001 again. And now, instead of doing op equal, we're going to do op equal verify. And so I want to highlight the difference between op equal and op equal verify. Op equal, if they're equivalent, well, whether they're equivalent or not, it'll return something to the stack, either 1 or 0. Op equal verify, the keyword verify is actually seen in a few different opcodes, and it almost always means the same thing, which means that if they are equivalent, then consume the data and don't return anything back. If they are not equivalent, or if they are false, then the script actually stops interpreting. Yeah, and it actually, like, the script stops right there. So as you guys can see, when I type in op equal verify, it's going to take in 1,001, 1,001, and it's not going to return anything this time. And yeah, whenever you see the word verify in any of the opcodes, it typically follows the same pattern. Okay, so now we're going to get a little bit more complicated. Let's go ahead and clear it again. And so now what I want to do is, let's have some fun by hashing something. So let's just type in the words opnext. And again, this is 6 bytes. So first we're going to be told, hey, stack, we're about to push 6 bytes to you. And now let's do one of the hashes. So let's do hash 256. Okay, cool. So now we're going to take opnext in byte format. We're going to hash it using hash 256, and we're going to see a result to the right. You can actually hover over this to see more information on it. So I'm actually going to take this hex that it spit out, which I'm not sure if that's correct. Or I'm not sure if what I'm copying and pasting is correct. Okay, for some reason it's not letting me copy this. Okay, cool. Here it is. So I'm going to go ahead and take this hash. Obviously, we know that it's equal, but if it weren't, and then we're going to check that they are equal. But again, we fully expect this to work. And the reason why I wanted to highlight this specific example is because this is actually a really good example of how hash locks work. So for example, if you wanted to have a UTXO that is only unlocked if someone provides a specific password or a specific word, this is actually how that would be done. So you see opnext, we typed in the word opnext, we did hash 256, and then we checked it against an existing hash already, right? So pretend we brought in that hash from elsewhere and they were equal. And so this is actually a really primitive example of how a hash lock would work. And now, last but not least, I want to show you guys exactly how, and again, we've gotten more and more complicated, but now I want to show you guys a transaction that's actually on mainnet. And I want to show you guys how we take the SIG script, the pub key script, we execute them sequentially, and how it's left at the end with a single number 1 in the stack. And so I'm going to go to the transaction to serializer. It's going to grab a quick example. And again, these are transactions that are on mainnet. Go back to my sandbox. We're going to grab this. This transaction is only 1 SIG script. So we're going to grab it. And I'm actually going to pause right here. And I'm curious to see how clever this audience is, who just by looking at the script here can tell what type of transaction this is. And obviously don't tell me that you saw it in the previous page, because I'm going to ask how you can tell. I've already answered a lot from you, so let's go with you back there. P2SH, it is not. How can you tell, Rob? Exactly. So
make sure to repeat the questions for the audience.
Yeah. So once more, I was asking here, how can you tell? Can anyone tell what kind of transaction this is just by looking at the script? And as Rob said, this is indeed a pay to public key hash transaction, and the clues are actually around lines 11, 12, and 13. So within those lines, we are seeing, hey, we're going to hash 160 something, which if you guys know, hash 160 leads to a hash that is 20 bytes long. Then we're telling the script, then we're telling the stack, hey, we're going to push 20 bytes to you. Line 13 is just some hash that is 20 bytes. And then again, I showed you guys op equal verify. We're going to verify that that hash actually matches a hash that we generate. And then last but not least, we're going to do op check sig. And again, obviously pay to public key hash. It's in the word key hash. The hash is done using hash 160. So Rob is fully correct. This is a pay to public key hash transaction. And again, if you know script, you could tell just by looking at the script here. So let's go every item line by line, walk through it, and then we're going to let it execute on the right, and then we can go ahead and wrap it up. So from the script sig, we first have op push 71. So obviously we're going to push 71 bytes worth of data. And just to give you guys a little answer there, that is a signature. Then we're going to push op push 33, which is a public key. So we're going to push 33 bytes to the stack. And then we're going to execute op dupe. So obviously we're going to duplicate that public key. Op hash, we're going to hash that public key. Op push 20, and then the hash, we're going to push some random hash that was found in the script pub key. We're going to check that the public key that we just hashed is equal to the hash from the script pub key. We're going to equal verify that they are the same. And if it's not, it's going to stop executing. And then again, like I mentioned earlier in this talk, almost all transactions, the last opcode you're going to see is op check sig, because again, we need a public key, we need a message. We're going to check that, we need to verify that the message is indeed correct and signed by this public key. So now if we go ahead and run this, I might need to forward a step. Okay, cool. We're going to see we're pushing the signature. We're now preparing and we're going to push the public key. We're now going to duplicate that public key. We're now going to hash this public key using ophash 160, which is going to lead to a 20-byte hash. We're then going to push the 20-byte hash that was originally in the lock script or in the script public key. We're going to verify, hey, the key that we just provided and that we signed with, is it equal to the hash of the public key that was in the lock script? It is. And then finally, we're going to do op checksig to check that the public key and the signature that we provided are indeed valid. And with that, I think I'm going to wrap it up unless there are any questions from the audience at this point. Okay, 2 questions, yes. There is, I think someone else can answer. I think it's 512 bytes, but I'm not sure about that. Do you know? For the stack? Yeah. 520 bytes. Okay, there we go.
In BitScript, some of the proposed opcodes to add to Bitcoin.
That is exactly what I'm working on, so that there is a playground for the upcoming opcodes. Yeah. In the sandbox. Yeah. Okay, cool.
From one last question from PodConf in the back.
Oh, I was just going to make the statement that I was incorrect earlier in saying that you can have multiple items on the stack. You can with legacy script, but in Taproot, you cannot.
There we go.
So there's more gotchas.
Yep, distinctions there. Another question up front.
Okay, I'm just curious, have you implemented all of this like yourself in your own code, or are you like somehow hooking into like the C++ core code, something like that?
Yeah, so this we actually wrote internally, though we were inspired by Burak's example of this, which I forgot the name of it. Yeah, Script Wizard, which is also similar to this. I actually wanted to understand these concepts deeply myself. So this wasn't built using a library or anything. This was built from scratch, so I could better understand exactly how everything works underneath the hood.